Hello students, Professor Nugent here. In this video, let's discuss some of the considerations in considering whether to use fixed effects or first difference. If you have just two time periods in your data set, then fixed effects and first difference are going to be equivalent, where we include a year dummy for the second period. However, if the number of time periods that we have in our data set are greater than or equal to 3, then fixed effects and first difference are not necessarily the same. And the difference comes down to the assumptions required. The main difference comes down to the assumptions required for the efficiency of the estimators. However, there are other considerations. So we're first going to look at serial correlation, but then we're also going to look at the relative size of the cross-sectional units to the number of time periods. And then we're going to think about potential bias. And this also comes down to whether our assumptions are valid. So let's first take a look at serial correlation. And we're going to make the assumption that n is much greater than t. And recall that we made this assumption as part of our setup for fixed effects. For n greater than t, if the u, I, t are serially uncorrelated, so this was our sixth assumption, our sixth fixed effects assumption. We assume that the covariance between UIT and UIS, and this is a conditional covariance, conditional on xi and ai, that this is 0 for t not equal to s. Alright, so we assume that the idiosyncratic errors are uncorrelated. There's no serial correlation. So if UIT are serially uncorrelated, then we discussed that the fixed effects estimator is the best linear unbiased estimator with the other assumptions, right? It is more efficient than, so it's more efficient than first difference. So you'll have smaller standard errors by using the fixed effects estimator. But what if this assumption is not valid? There are two potential outcomes. If the errors are serially correlated, so if we have serial correlation, and the UIT follow a random walk, a random walk is given by the following process. UIT is equal to UIT minus 1 plus ET. So the current idiosyncratic error is equal to the past idiosyncratic error plus some random error. So the expected value of ET is equal to 0. Variance of ET is equal to sigma squared E. Then in the first difference estimator, in this case where we have serial correlation, delta UIT would not be serially correlated. So let's look at this. If we have a random walk, then taking the first differences fixes the serial correlation where the serial correlation is characterized by a random walk. So in this case, the fixed effects estimated, the first difference estimator is going to be better than the fixed effects estimator because there is no resulting serial correlation in the errors. However, if the serial correlation is not as strong as a random walk, then it's going to be hard to compare the efficiency based on this criteria. We can typically expect unobserved factors that change over time to be related. And so we can typically expect for assumption number 6, that is, we can typically expect this assumption to be invalid. And so whether we are in the first case where we have a random walk, or in the second case where we have something less than the random walk, is not clear. And we may have to test for it. And it may come down to running both estimators and comparing the results. Let's look at some other ways to compare the two estimators, fixed effects and first difference. If we have that t is much larger than n, then inference with fixed effects is very sensitive to violations of the classical fixed effects assumptions. Assumptions 1 through 7 that we have previously discussed. Whereas the first difference can rely on the central limit theorem and asymptotic results because the first difference transforms an integrated time series into a weakly dependent process. So if you have more time periods in your data set than you do cross-sectional units, then inference with your fixed effects could be very sensitive to violation of the classical assumptions. This is a second consideration, and a third consideration is that for assumptions that result in bias of the estimators, so where we have potential bias, such as the strict exogeneity assumption, the fixed effects estimator is likely to be less biased. With t greater than 2. And that is because the bias in the fixed effects estimator tends to tends to 0 at a rate of 1 over t. Whereas the bias and the fixed difference, the first difference estimator does not depend on t. Alright, so that's it for comparing fixed effects and first difference. Stay tuned to the next video. We will introduce the random effects model.